Space Science 63 with John Fitch is a presentation of the National Aeronautics and Space Administration. Today's program, Laboratories in Space.
Hello, I'm John Fitch, and this is Nimbus. And Nimbus is a weather satellite. The first of its kind will go into orbit sometime in the next 6 to 12 months. Now, in this program, we're going to be talking about Nimbus and some of its many, many cousins, the instrumented satellites. Actually, we could probably spend the whole half hour just naming all the satellites that are in orbit or the ones that are being readied for future experiments. There are so many of them that I admit it does seem confusing at times, but maybe it would be a little clearer if we sort of group them into 4 main categories. I guess the one we're most familiar with is manned spaceflight. Project Mercury, that was 1 man in orbit around the Earth. Project Gemini, 2 men going around the Earth. And finally, Project Apollo, which will send 3 men to the moon and back. Then there are the deep space probes like Ranger to the moon, and Pioneer in orbit around the sun, and of course Mariner, which sent back such interesting information about the planet Venus. The rocket soundings don't go into orbit, of course. These are instrument packages which are hoisted aloft on rockets, gather information, and send it back to Earth. And finally, our subject for this program, the unmanned instrumented satellites. And these fall roughly into 2 categories, the application satellites and the scientific satellites. Many of these instrumented satellites are being planned and tested out at the Goddard Space Flight Center in Greenbelt, Maryland. And we're very fortunate in having the director of Goddard, Dr. Harry J. Gett, to tell us about some of these satellites. Dr. Gett, it seems to me with so many of them that some of these programs must overlap or even duplicate other programs. For instance, we have weather satellites like Tyros and Nimbus.
Well, it is true that both Tyros and Nimbus are weather satellites, but Nimbus is a much improved version of Tyros. For instance, it has the same relationship to Tyros as you might say the DC-3 airplane had to the Wright brothers airplane at Kitty Hawk.
Oh, I see. It's really an advanced version, then.
That's so.
Well, now, we have a model of Tyros. Perhaps you could explain to us how it works.
Yes, this is a half-scale model of Tyros. It's up in orbit now. We have 2 of them up in orbit at 400 miles above the Earth. And it spins about this axis, and when this surface looks down, here we have a camera which looks down on the Earth and takes a picture of the cloud cover. It takes a picture on a, what in effect is a television tube, very similar to the tube that you have in your home television set, except that it's a sticky tube.
Oh.
And for the 2 seconds that it holds this picture, we scan it. We pick off electrical impulses, which are then recorded on this tape recorder here. And then when the satellite comes back over our ground station, it's possible to transmit the signal that is stored on this tape recorder down to the ground.
Now, when you get it back to the ground, then how do you put the picture back together again?
Well, of course, then we have a bunch of electrical impulses, and we put it back together in a manner that's very similar to the operation of this facsimile machine that has been in use for years on Earth here for transmitting pictures to a distance. Mm-hmm. The electrical signal actually is put into the machine. It is then reconverted back into a picture, into light impulses. And out of it, we get a picture. For instance, here is a picture that was developed as the satellite passed over the Mediterranean. As you can see here, the Mediterranean, the Nile, and the Red Sea.
It's very clear.
Yes, if anybody had any questions in their mind about the accuracy of the geography books, you can see here that they're right. But now we get a series of these pictures, 32 of them in sequence, and by putting these pictures together, you can get an idea of to the general cloud pattern over this region of the Earth. Here is a typical one, and I happen to have selected one which shows the development of a hurricane.
Now, isn't it true that Tyros actually gave us our first indication of that tremendous hurricane? I think it was Esther back in 1961.
This is so. As you see, we purposely launching these satellites during the hurricane season so that they can do precisely this. And hurricanes generally are born in the Atlantic west of Africa. Mm-hmm. And Tyros actually did observe Hurricane Esther and other satellites some 2 or 3 days probably before they would have been observed by any other means.
That can be very valuable then to someone who wants to protect his property, getting that additional warning.
Yes, indeed.
Well, now, if Tyros works so well, why do we need Nimbus?
Well, trouble with Tyros is that it only spends less than 25% of its time looking at the Earth. And we want to make it so that our next satellite spends 100% of its time looking at the Earth. I have to go over here and show you on this globe why Tyros works in this way and what we hope to do in order to fix it up. Mm-hmm. As you recall, earlier when I showed you the model of Tyros, I said it was spinning in orbit, which means that it's like a gyro up there, and it looks at a given region in space then all the time. So as it passes over the Earth here, at this point in orbit, the camera is looking down on the Earth, mm-hmm. and therefore, if the Earth is sunlit at this time, it's possible to take a picture of it. But now as it passes over on this side, as you can see, the camera is looking out into outer space. Oh. So obviously we can't take any pictures. Comes back again, and then when it gets on this side again, it is looking at the Earth.
So what you'd like is a satellite that'll look at the Earth all the time.
That's right. We want a satellite that will go around the Earth and look at it like this.
Mm-hmm. Now, how are you going to be able to do that?
Well, as you can appreciate, in order to do that, we have to do two things. We have to do something which will tell the satellite where the Earth is, and then secondly, we have to give it some muscles so that it can nudge the satellite around and make it look at the Earth. I think in order to show you how we do that, I have to take you over here to this full-scale model of Nimbus, which we hope to launch within a year from now. Mm-hmm. Now, the way Nimbus knows which way is down, in other words, which way the Earth is by means of this horizon sensor up here. This horizon sensor will tell the difference between where the Earth starts and where space begins. Mm-hmm. It transmits a signal to the control system of Nimbus, which consists of inertial wheels here and these jets. And by these inertial wheels and jets, we can nudge Nimbus so that it can, in fact, keep looking at the Earth.
Now, if it's looking at the Earth, how does it get its power from the sun? Because it won't be pointed towards the sun.
Well, as you can see, these are the solar panels which get the power from the sun. And what we would like to do is keep them perpendicular so that the sun shines right down on them this way. What we do is that we have a shaft here, and they can rotate around this shaft. And they'll have a sun sensor on it so that they will rotate with respect to the satellite, but always stay oriented with respect to the sun.
Well, that pretty well tells the story of our weather satellites. And what about the rest of our applications program?
Well, the other part of the applications program that is close to application is the communication satellites. Mm-hmm. If we go over here, we have a few models of the communication satellites that we have launched. This one, as you will recognize, is a small-scale model of Echo, which was that 100-foot sphere that was launched.
You can still see that, can't you?
Every once in a while, if you look in the right direction in the sky, you can see it. Now, Echo is a passive communication satellite. Now, what this means is that all it does is reflect the radio waves. The station will transmit, say, from the East Coast here. It can't see the station on the West Coast because of the curvature of the Earth. But it can send a radio beam up here, can bounce off, and can be intercepted by the station on the West Coast. Mm-hmm. Now, in distinction to this passive satellite, we have the active satellites represented here by Relay, here by Syncom, and then, of course, there is Telstar, of which you have also heard. The difference between these satellites and this one is that they're active because they not only intercept the beam and reflect it, but also they amplify it and they transmit back.
They have their own little transmitter.
That's right. Now, there are two types here. One is relay, which is very similar to Telstar. It's characteristic that it's been put into a low Earth orbit. In order to get constant contact, communication contact, we'd have to put some 30 of these satellites in orbit at a time. What CENTCOM tries to do is to put the satellite up much higher into what we call a synchronous orbit. Now, this means it goes around the Earth just once every 24 hours instead of once every 90 minutes, as this one does. And if we get this located just above us all the time, or halfway between us and Europe, it will stay up at this portion of the sky, and we'll be able to transmit to it and from it constantly.
I see. Isn't it true that some of these applications, satellites, also carry scientific experiments which have nothing to do, say, with the communications?
This is so, although this is sort of a byproduct. You see, in the first place, in order for these satellites to be economically feasible, they have to last for some 5 years. So we send up some instruments which will tell us what is the environment they're going to be exposed to, what will be the damaging effect of the particles. But our scientific exploration of space, we really do from a completely different set of satellites which are specifically made for this purpose.
Well, now, what is it that we're trying to find out?
Well, probably best to go over here and look at this simplified map of space, which shows you the various areas of interest to us. And they really can be divided into 3 areas. We know that what goes on up at the sun affects us very, very importantly down here at Earth. So our one objective is to get some satellites up above the atmosphere here so that we can look at the sun and that we can observe what is going on up there. We do know is that every once in a while the sun puts out a big solar flare. These are huge explosions on the face of the sun. You can get a better feeling for just what they are from a look at the film clip we show here. And what our objective is now is to look at these explosions in considerably greater detail to determine what are the temperatures inside them, what are the magnetic fields, and what the like that produce them. Now, they do spew out, we know, a magnetic field and a particle and plasma flow out into this region here, which we call interplanetary space. Now, in order to better understand just what they do throw out, we have another set of satellites which operates in this interplanetary space region and samples these particles. Now, the third region is that surrounding the Earth. As you know, the Earth is not only surrounded by the atmosphere, which to a certain degree shields it from these particles, but it also is surrounded by magnetic field lines coming from the Earth's magnetic field, and we call this a magnetosphere. Now, this magnetosphere acts as a huge magnetic shield, and these particles come and bounce off it. Some of them come on and penetrate down in, hit the upper atmosphere, and in so doing, create a new set of particles which become the population of the Van Allen radiation belts we have all come to know. It is our objective then to investigate the population of this Van Allen belt, but more importantly, to determine where these particles go, because we do know they follow the field lines down and up in the polar regions. They impinge on the ionosphere and the upper atmosphere. In so doing, they heat the upper atmosphere, and we think they are the cause of the changes in weather. So as you can see, we have 3 regions that we want to look at. One, the sun itself. Second is the interplanetary region and what goes on there. And third is the magnetosphere.
Now, can you give us an example, say, of a satellite that would be used to study the region near the Earth, this magnetosphere?
Well, one of them is this satellite, of which we have a small-scale model here. This is the aerial satellite known as the International Ionosphere Satellite. It has the international tinge to it because it, in fact, was built at Goddard but the 8 experiments that are on board it were furnished by British experimenters. Now, these experiments were designed to investigate the characteristics of the upper ionosphere, how many electrons are up there, what is the electron temperature, how this varies with solar events, because we can observe fluctuations in it. Here in this little ball up here was a magnetometer, which told us something about the magnetic field there. Now, it is from satellites such as this, and there have been a number of others, launched into the ionosphere or upper atmosphere, that we are studying this particular region.
And what about satellites that would be used to study that interplanetary region that you mentioned?
Well, here is an example of this. This is Explorer 10. This satellite was launched and went up to an altitude of some 185,000 miles, which took it well beyond the influence of the Earth's magnetic field.
That's more than halfway to the moon, isn't it?
That's right. Now, obviously out there, the magnetic field is of much lower value than the magnetic field is here. For instance, it's 60,000 times here the value that we expected to find up there. Therefore, in this ball up here, there was a rubidium magnetometer, which could measure very, very low magnetic fields. And in this portion of the satellite, separated from the ball so that it wouldn't influence the magnetic field up here, were energetic particle experiments. Now, a typical energetic particle experiment is a Geiger counter, which counts the number of particles. Well, there are different ones. So with this, we're able to determine what goes on in interplanetary space. And we were very, very fortunate that when this was out there, a solar event occurred. And we were able to sense first the quiescent condition in the absence of a solar event, and then the very turbulent fluctuations in the magnetic field and the energetic particles that were carried along with it.
Well, now, what about the source of these disturbances, the sun itself? That was the third item that you mentioned that you wanted to study.
Yes, we study that from the orbiting solar observatory, one of which has been up there for a year now. Now, this is a full-scale model of the orbiting solar observatory.
Well, tell me, Dr. Gett, I mean, we can see the sun perfectly well from right here on Earth with telescopes and other means. Why would we need an orbiting observatory?
Well, in order to explain that, I think I have to go over to this little setup over here and demonstrate what the Earth's atmosphere does to the sun. In the first place, let's assume that this little light here is the sun. And as you can see, it not only puts out visual radiation, which we can see, but it also is putting out some ultraviolet radiation, which we're measuring right here. Actually, we have an ultraviolet sensor here, and this needle shows the amount of ultraviolet radiation that is impinging on it.
All right.
Now let's then take this little piece of glass and simulate the atmosphere with it. Now, if I put this glass in front of the light, you can still see the visual radiation through there.
Right.
But on the other hand, when I put it in front of the light, you can see from watching that meter that it cuts off the ultraviolet radiation.
Right. Dr. Gett, does the atmosphere filter out other types of radiation besides this ultraviolet that you've mentioned?
Yes, it filters out all the shorter wavelengths, which means that in the X-ray region and in the gamma ray region, as well as the ultraviolet, this radiation is filtered out.
So that's why you have this orbiting observatory, which I gather will be able to measure these radiations from the sun.
That's right. This orbiting observatory, its purpose is to point the instruments which are in this particular part of the satellite at the sun. Now, the way this is done is that this, once again, is a gyroscope in space. This particular portion of it rotates at about 30 RPM. Whenever it drops below this rate of rotation, some little jets of compressed nitrogen that are in this bottle here speed it up. So this means that this whole vehicle here is stabilized in space, and you will notice that this portion of the vehicle. The upper portion is, in effect, what we call a sail. This is not rotating, but this is.
I see.
So now we have a platform in space, and there are jets up here which can precess this around so that in the end it ends up with this section of the instrument here pointed at the sun. And this portion of the satellite has a number of different experiments that will look at the sun in the different wavelength regions and tell us what's the temperature, or tell us, for instance, is there iron or helium or what have you that is causing in these areas that they're looking at. Now, in addition, there are some experiments in the wheel, which is rotating, which every time it comes around at this point, we'll be looking up at the sun.
Well, what happens when this goes around behind the sun?
Well, that's a good...
Behind the Earth is what I really mean.
Good point here, is that every time it goes around and behind the Earth, it loses sight of the sun. This means it has to point at the sun again. So once every 90 minutes, it has to point back at the sun. And this is a fairly neat trick because pointing at the sun at this distance is about the equivalent of pointing at a beach ball at some 2 miles distance. And this orbiting solar observatory has succeeded in doing this someplace between 5,000 and 10,000 times during the year of its existence.
Amazing. Now, I've also heard this referred to as a streetcar satellite. What does that mean?
Well, you appreciate that the previous satellites that we have talked about, they were sort of special purpose satellites. They were specially designed for a given purpose. In contrast, this one here carries some 13 different experiments. We intend to launch it at about a rate of once a year with a different set of experiments.
All right, so it comes around like a streetcar.
That's right. The analogy is that the other ones are like taxis, which go to a special place and just specially for this purpose. This one will run a given route, which will be to the sun in effect, and will be peopled by different passengers each time it is launched, every year that it's launched.
Well, are there other streetcar satellites besides this one?
Yes, there are, and just like streetcars which run to various points, each one of these observatory satellites has a different purpose. This one has the sun, as is clear. Now, this one over here, the streetcar satellite that runs out to interplanetary space or the magnetosphere.
It's a pretty strange-looking contraption.
Well, now, the reason it looks like such a Rube Goldberg contraption is that because it does carry between 20 and 30 experiments, but these experiments want to do different things, and they want to look out in different directions. We have a set of experiments that will be down in this end. This end will be pointed at the Earth. So in this end, we will put the experiments that want to look at the Earth. Now, in these boxes here, see, we always have to keep these solar panels pointed at the sun. So here, we'll put the experiments that want to look at the sun. Here, we put the experiments that want to look in the direction the satellite is moving, in the orbital plane. Here, the satellites that want to look back. And here are the satellites that want to look out, or the experiments that want to look out in still another direction. This particular one here carries a magnetometer, and it has to get far away from the rest of the magnetic elements in the satellite here so that we be sure we're measuring the magnetic field of interplanetary space, not the vehicle. You can well imagine that we can't launch a vehicle of this nature in this particular configuration. So actually, it is, as you can see, it's a very complicated folding mechanism, which all these will fold together. These things will pull in, and they will be launched in a folded condition. And then when they get into space, they will be deployed.
Are there still other kinds of observatories?
There's one other type of observatory, which is over here, and this is directed at a region of space that I haven't yet mentioned. You notice all my discussion so far has concentrated on the solar system. Now, the purpose of this observatory, which is the orbiting astronomical observatory, is to look out at the stars. First thing I should say is that this is a relatively small-scale model of it. This particular section here will stand some 10 to 12 feet high. And really what we have here is the objective of this orbiting astronomical observatory is, in one sense, the same as the objective of the Mount Palomar Observatory. Now, obviously, we don't carry a 200-inch telescope, but we do, in effect, carry a 30-inch telescope in here. And what we have to do is the same as you do on the Mount Palomar telescope. We have to point this accurately at the stars with a very, very high degree of accuracy. So there's quite an engineering problem of designing this spacecraft so that you can point accurately and hold this accuracy over long periods of time.
When discussing some of these more advanced satellites, it seems to me, Dr. Gett, that you have mentioned that we take what we learn from one set of experiments, one set of satellites, and use that information in designing the new satellites. Is that true?
That's true. It seems to be true of any area of research, and it's surely true of space research during this time when we're sort of in the exploratory era, is that we find out a lot of things, but in the process we spawn a lot of new questions as a result of what we have found out. For instance, the Orbiting Solar Observatory has already told us a lot about the sun, but we're just aching to get another satellite up there so that we can look at specific regions of the sun to see where these high temperatures are located that it has detected.
Earlier, you pointed out the International Satellite Aerial, which I believe is in cooperation with the United Kingdom. What about some of the other countries? Are we going to have an international program in that respect?
The work we're doing in space is a lot more of an international venture than most people realize. It not only includes the cooperation on the satellites themselves, such as the cooperation with the British, but here is another example of a second satellite in which the Canadians built it, we launched it, and it's up there, but really the broad-based cooperation is that there are many ground stations in a number of countries that are receiving the data that is transmitted from these satellites, and the scientists in these countries are actually in a position to analyze these data. You also will get a feeling of this from the fact that now at Goddard, in order to do our job and receive the data from our various satellites, we have some 30 ground tracking stations located in 14 countries throughout the world. And this is quite an extensive international cooperation.
Well, thank you very much, Dr. Gett. Well, I think you can see that we've certainly come a long ways in the last 5 years from this little grapefruit called Vanguard 1 to the tremendous Nimbus weather satellite. I wonder what the next generation will be like.